Good morning, my dear friends. I hope you all are doing great. May God bless you all. Let's get started. Today we will be talking about the formation of sucrose molecule. Have a look. For this thing we need monosaccharides, two monosaccharides to make sucrose, because sucrose is a disaccharide. We need alpha D glucose. So let me draw the structure of alpha D glucose first. So this is your, let me draw it here. This is alpha D glucose for you. Alpha stands for the position of OH group on right side, or we can say downwards, correct, or below at carbon number 1, which is anomeric carbon. So that means OH group will be down at first carbon, because first carbon is here anomeric carbon, and rest of the structure is HOH, second carbon. Third carbon will be OH group on the left side. Left side basically means up, right side means down, H. So here, my dear friends, we'll be having H, OH, H, and then finally we have CH2OH. That is the sixth carbon, fifth carbon, fourth carbon, and third carbon. This is our alpha D glucose molecule. Now in your book, if you see that they have inverted the structure of fructose, but we are not going to do that. I will show you that how can we represent it in a very simple way. Let's talk about beta D fructose. Let's write down beta D fructose down here. Beta D fructose. Okay guys, have a look. For beta D fructose, everybody should understand that I need a ring called as furon. For fructose, I need a furon ring, correct? And it's a beta form. Beta form means the OH group will be up. And up means basically what? On the left side, right? OH, and here we'll be having one. First carbon will be outside, so it will be CH2OH. That's one. And this is second carbon, is anomeric carbon here. And third carbon, everybody knows OH and H, OH, and finally we have H, and at last we have CH2OH. And this is the sixth carbon, fifth carbon, fourth carbon, third carbon. Correct? This is our beta D fructose. Now between alpha D glucose, this molecule, and beta D fructose, there is a bond formation. There is a bond formation at between carbon number first of glucose and carbon number second of fructose. Here the carbon number first is anomeric carbon, and here the carbon number second is anomeric carbon. So this bond is formed between two anomeric carbons, carbon number 1 of glucose and carbon number 2 of fructose. This bond is formed. So let's take it out. So there is a loss of H2O molecule. So it's a condensation reaction. So let me call it as a condensation reaction, because there is a loss of water molecule. Now have a look here. I have to draw the structure right now. So it will be like this now, the linkage. Let's draw the alpha D glucose first. Let us draw the beta D fructose second. Correct? After that, there is a link between the interaction between first carbon and second carbon. First carbon of glucose and the second carbon of fructose, there is a link. There is a formation of glycosidic bond by the loss of H2O. So what remains here? Here is a carbon we have. Here we have a carbon. Okay. What is remains here? Oxygen. H2O is lost. So what remains here now? Carbon. So first carbon will react with the second carbon, but between them there will be oxygen. So it will be like this. First carbon will react with the second carbon, but between them there is oxygen. Correct? So it will be CO and C bond, because OH and H will come out in the form of water. Correct? Now my dear friends, what is the remaining? The first carbon will be here only CH2OH, that is the first carbon, and here we have actually H, and then we have HOH, then we have OH, H, finally HOH, H, and finally CH2OH. Correct? Here we have OH, H, OH, this is third carbon, fourth carbon, fifth carbon is H, and the sixth carbon is CH2OH, the sixth carbon. Second, third, fourth, fifth, sixth. So this bond which I am talking about here, this bond is nothing but it is a glycosidic bond. Okay, please remember this COC bond is a glycosidic bond. Okay, before that I will mention here this molecule is sucrose molecule. So it is between the first carbon of glucose and the second carbon of fructose. First carbon of glucose is anomeric carbon, and here the second carbon of fructose is anomeric carbon. So this bond is formed between anomeric carbons, and we have a COC bond. I will call this bond now as glycosidic bond. Glycosidic bond. And this glycosidic bond can be also written as, you know that it is between alpha and beta. It is not between alpha and alpha, beta and beta. This bond is formed between alpha and beta, alpha glucose and beta fructose. So here I will write down it is alpha comma beta, and it is between first and fourth carbon or first and second carbon. It is between first and second carbon. So I won't write down 1 and 4. I will write down 1 comma 2. Because it is between first carbon and second carbon. Alpha is for glucose and beta is for fructose. If it is between two alpha molecules, then only alpha I have to write down. If it is between two beta molecules, then only beta I have to write down. But if it is between alpha and beta, so I have to write down alpha beta. 1 comma 2 between first carbon and second carbon. Which bond is this? Glycosidic bond. So my dear friends, this is our alpha beta 1 comma 2 glycosidic bond. I hope you have understood that I took alpha D glucose molecule and beta D fructose. Okay, then there was a loss of water molecule because first anomeric carbon, that anomeric carbon, first carbon in glucose, okay, reacts with the second carbon of fructose, and that second carbon is also anomeric carbon of fructose. So two anomeric carbons are reacting, they are losing water. Then there is a formation of COC bond. I will show you that COC bond, and that COC bond is the glycosidic bond. You can also call it as alpha beta 1 comma 2 glycosidic bond because it's between alpha and beta sugars, and it is between first carbon and second carbon. So alpha beta 1 comma 2 glycosidic bond. So this is exactly the sucrose structure, disaccharide structure. Please make a note of this particular thing. So my dear friends, we are done with the formation of sucrose. Okay, now we'll be talking about reducing and non-reducing sugars. Okay, I have taken this topic little later. Why? Because you have to understand certain basics first, then only you can understand what reducing and non-reducing sugars are. So let's go with this particular concept. Reducing sugars, first of all, those sugars which can reduce Tollens reagent and Phalenx solution are said to be reducing sugars. Those sugars which can reduce Tollens reagent and Phalenx solution. Now one question will come into your mind, what do you mean by reduction? How the Tollens reagent is being reduced and how the Phalenx solution is being reduced by the reducing sugars, correct? That thing will come into your mind. First of all, let us understand who can reduce. Later I will answer this particular question. All monosaccharides, like in monosaccharides you have glucose, you have fructose, you have arabinose, you have dihydroxyacetone, okay, you have ribose, and many more. These all are monosaccharides, and these monosaccharides are basically our reducing sugars. Means these sugars, if you take glucose, fructose, arabinose, dihydroxyacetone, ribose, etc., these molecules, these monosaccharides will reduce. They will reduce Tollens reagent and Fallings solution. So they can reduce Tollens reagent and Fallings solution. Okay? Keep in your mind that sir is going to tell you what is this reduction all about later. Second thing, disaccharides can also act as reducing sugars, but except sucrose. Sucrose is a disaccharide, but it is not the reducing sugar, it's non-reducing. So disaccharides you will be having them maltose and lactose. These two will be reducing sugars. And this sucrose is a non-reducing sugar. That's why I wrote except sucrose. Except means sucrose is not a reducing sugar, but these two disaccharides are reducing sugars and all monosaccharides are reducing sugars. So my dear friends, all monosaccharides and disaccharides are reducing sugars, but in disaccharides you have sucrose molecule. That sucrose molecule is basically non-reducing sugar. So let us explain about non-reducing sugars after this. So my dear friends, we spoke about reducing sugars. Those sugars which can reduce Tollens reagent and Fallings solution are said to be reducing sugars. All monosaccharides and disaccharides are reducing sugars, but in disaccharides you have sucrose molecule. That is not a reducing sugar, only sucrose I am talking about in disaccharides. That is a non-reducing sugar. So let's have a look at non-reducing sugars. Those carbohydrates which cannot reduce Tollens reagent and Fallings solution are said to be non-reducing sugars. So in non-reducing sugars you have only one disaccharide here. This is a disaccharide, sucrose. Only one example. Because maltose and lactose are reducing sugars. I have explained you that. And polysaccharides, you have glycogen, you have cellulose, okay, and you have starch. These are also non-reducing sugars, means polysaccharides and the sucrose molecule, which is a disaccharide, do not reduce Tollens reagent and Fallings solution. Okay, all monosaccharides and disaccharides except sucrose are reducing sugars because they can reduce the Tollens reagent and Fallings solution. So my dear friends, okay, you have gotten the information about reducing and non-reducing, but let me explain you in little detail that how does it happen, how they are called as, or why they are called as reducing sugars and all. Please make a note of this. So my dear friends, in order to make you understand what this Tollens reagent is all about, so let me take some time to explain you what this Tollens reagent is all about. So I will give you a crispy idea about it. It will be helpful for you. First of all, I have taken Tollens reagent. What is Tollens reagent? We will directly come to the molecule here. Diamine cellular first nitrate. So here we have diamine, 2 times NH3, that is diamine. This is cellular and this is nitrate. So diamine cellular nitrate. Why we are writing cellular first nitrate? Because cellular is losing 1 electron which goes to nitrate. So it's diamine cellular nitrate. This is our Tollens reagent. So what is the role of Tollens reagent? I told you that sugars can reduce. Which sugars? Reducing sugars can reduce Tollens reagent, correct? Reducing sugars can reduce Tollens reagent. So first of all, let us understand, I will take on an aldehyde here. I am taking on an aldehyde, correct? Because our monosaccharides will be mainly having aldehydes, okay? Or they will be having alpha hydroxy ketonic groups. So let us understand first of all, what does Tollens reagent do? If you have an aldehyde with you, okay, then I am using the Tollens reagent. If I use the Tollens reagent, what happens? This aldehyde is oxidized to carboxylic acid. So that means you will be getting RCOOH. That means aldehyde has been oxidized. So oxidation has taken place for aldehyde, has been oxidized to carboxylic acid. But what will happen to the Tollens reagent? Let's understand. In Tollens reagent, I have diamine silver first nitrate. This is my molecule, which is Tollens reagent. Aldehyde undergoes oxidation to form carboxylic acid. Correct? But Tollens reagent should be reduced. This aldehyde will reduce the Tollens reagent. How? Have a look. From this molecule, we have a silver. The silver is in the form of Ag+1. Oxidation state is +1. But when you look here in the product side, I am getting Ag. What is the meaning? When aldehyde interacts with the Tollens reagent, okay, aldehyde undergoes oxidation and gives me carboxylic acid, correct? And in Tollens reagent we have silver. Silver's oxidation state is +1. Okay? When this Tollens reagent converts aldehyde into carboxylic acid, okay? From this Tollens reagent, the silver +1 is converted into silver. And that silver is nothing but it is a precipitate, PBD, it's a precipitate. Okay, it settles down or it will stick to the surface, the internal surface of a test tube in which reaction is taking place. So this silver which is produced in this reaction will stick to the surface of the test tube in which reaction takes place. So now look here, in Tollens reagent silver was in +1 state. But from the product side, the silver's oxidation state is 0. This precipitate is also known as silver mirror. This is also known as silver mirror. Okay? Because this silver will stick the internal onto the internal surface of a test tube, and it will be the silver mirror precipitate. Now look here. The oxidation state of silver goes from +1 to 0. That means decrease in oxidation state. And decrease in oxidation state or oxidation number is known as reduction. So what is happening for silver +1? Silver +1 goes to silver 0. That means silver undergoes reduction. Who has reduced the silver? Aldehyde. And what has happened to the aldehyde? Aldehyde has undergone oxidation and changed into carboxylic acid. Correct? But aldehyde has reduced the silver from +1 to 0. Silver has changed from +1 to 0. So I will write down here in this process, aldehyde, okay, reduces Ag+, or we can say it reduces silver. Let us write down silver. It reduces silver from +1 to 0 oxidation state. Because everybody among you does know that reduction means decrease in oxidation number. So +1 to 0 means decrease in oxidation number. So aldehyde reduces silver from +1 to 0 oxidation state, and that is nothing but that is reduction only. As I told you, reduces. So I hope, my dear friends, you have understood this factor. Same thing will happen to the glucose molecule, because glucose molecule also contains aldehyde group. Correct? If we use Tollens reagent, what will happen? The aldehyde group of glucose will change into carboxylic group. Have a look like this. And in this case also we can mention that aldehyde itself gets oxidized to carboxylic acid. I will write down aldehyde is oxidized to carboxylic acid by Tollens reagent. So your Tollens reagent is oxidizing the aldehyde to carboxylic acid. I hope you have understood, my dear friends. From Tollens reagent I am taking silver, which is in +1 state, and when from the product side I am getting a silver mirror which forms the inner lining of the test tube. Okay, that's a precipitate. It settles down onto the inner surface of the test tube. Oxidation state of the silver is 0. So silver has gone from +1 state to 0. So that is decrease in oxidation number. We can also call it as this thing as decrease in oxidation number. Oxidation number. And decrease in oxidation number is reduction. So your Tollens reagent has undergone reduction, because silver belongs to Tollens reagent. Who has reduced the silver from +1 to 0? Your Tollens reagent or your aldehyde? Aldehyde has reduced the silver from +1 to 0. Correct? So this aldehyde has become a reducing compound. You can't call it as reducing sugar because it's not a sugar here. But if I take in place of this aldehyde as a sugar molecule like glucose, then it will become reducing sugar. Correct? Have a look here. Let me remove this and let me use here CHO, then CHOH 4 times, then CH2OH, and this molecule is our glucose. It has an aldehyde. This is aldehyde group of glucose. Correct? So I will be getting here a carboxylic group only, but it will be in this format now, COOH, then you have CHOH 4 times, then CH2OH. Now this is our carboxylic acid. This is our carboxylic acid. So the aldehyde group of glucose, okay, is oxidized, shows oxidation, or is oxidized by which thing? Tollens reagent into carboxylic acid. You can see this is the carboxylic acid. So look here, aldehyde is oxidized to carboxylic acid by Tollens reagent. Second factor, this glucose, the aldehyde group I mean to say, not the entire glucose, the aldehyde group of glucose, this one, aldehyde. This aldehyde will reduce silver from +1 to 0 oxidation state. So this glucose will become our reducing sugar because it has reduced the silver from +1 to 0. So remember, what are reducing sugars? Which can reduce the Tollens reagent. How they are reducing the Tollens reagent? They are reducing actually the silver component of Tollens reagent from +1 to 0 oxidation state. Okay, so I can call it as the reducing sugar glucose molecule. I hope you have understood this particular example. Please make a note of this. So my dear friends, let's have some idea about the Fallings solution as well. If you talk of Fallings solution, it's prepared by combining two separate solutions. So for preparing Fallings solution, you need two separate solutions. The first one you need is copper sulfate, that is solution, copper sulfate solution. That's called as Fallings solution A, and it is blue in color because of the presence of copper ions, correct? Look here. Then you need another one, Fallings solution B. When you mix Fallings solution A with Fallings solution B, that is your Fallings solution basically. So Fallings solution is actually the combination of two Fallings solutions. Fallings solution A plus Fallings solution B. Fallings solution A is copper sulfate. Fallings solution B is potassium sodium tartrate, which is colorless. When you take Fallings solution B and mix it with copper sulfate, which is a Fallings solution A, then you will be getting a resultant complex formation is there. That complex is known as bis tartrate complex of copper. So when you combine Fehling solution A with Fehling solution B, that means you are combining copper sulfate, you are making it to react with potassium sodium tartrate, which is also known as Rochel's salt. You can also call it as Rochel's salt. Correct? After their combination, you will be getting a complex that is bis tartrate complex of copper. That means copper will interact with the tartrate. Tartrate basically comes from here, potassium sodium tartrate. Okay? Bis means there will be two molecules of tartrate in combination with copper. You please try to understand that a copper complex is being formed. Correct? So what is the role? Let us understand after that what is the role of this particular complex. And this complex is your Fehling solution. And remember, this complex contains copper plus 2 ions. So copper plus 2 ions are present in Fehling solution. Once again I am telling you, Fehling solution is a combination of two solutions. Fehling solution A, Fehling solution B. When you combine copper sulfate solution with potassium sodium tartrate solution, then you will be getting a particular complex called as bis tartrate complex of copper, and this bis tartrate complex of copper is your Fehling solution. And remember, in this Fehling solution, copper ion plays an important role. I hope you have understood this particular thing. Please make note of this. So let's talk about our sugar molecule. Okay, this is our aldehyde in a sugar molecule. Okay, so I am using the Fehling solution. And everybody knows that this Fehling solution contains, what is it actually? It's a bis tartrate complex of Cu plus 2 ions, plus 2 ion. That means this Fehling solution or Fehling solution will give me copper ion. This copper ion I need. Correct? So what is happening? The same thing will happen. This aldehyde will be oxidized. Let's oxidize this aldehyde. Aldehyde group will be oxidized into carboxylic acid. So oxidation is taking place here. Correct? So your aldehyde is converted into carboxylic acid. Carboxylic acid. Let's write down the rest of the molecule. CH-OH 4 times and then CH2OH. Correct? Now this is my glucose molecule. In this glucose molecule, what we have basically, okay, let me write it down. This particular name I will write down to show you that aldehyde undergoes oxidation. So to show you that aldehyde shows oxidation. On the other hand, as I told you that in Fehling solution we have a complex called as bis tartrate complex of Cu plus 2 ion. Correct? Now my dear friends, aldehyde is showing oxidation to carboxylic acid. Who is oxidizing the aldehyde? Aldehyde is oxidized to carboxylic acid. Who is doing this? The Fehling solution. So my first point is that Fehling's solution oxidizes aldehyde to carboxylic acid. And this aldehyde belongs to glucose, sugar. So the aldehyde of glucose molecule is oxidized to carboxylic acid by the Fehling solution. Now what happens later? The one more product you are getting here, which is basically the cuprous oxide. This is cuprous oxide. Okay? And that cuprous oxide in which the copper will have oxidation state. I will take one copper out its oxidation state is +1. The oxidation state of this copper in cuprous oxide is +1 because it's cuprous. And this is basically a red precipitate, red PPT. Now when I take out this copper, the oxidation state of copper is +1. Now look here, you are going from +2 to +1. +2 to +1 is nothing but decrease in oxidation state. Decrease in oxidation state. And decrease in oxidation state is basically reduction. So which thing is undergoing reduction? Copper +2 ion is undergoing reduction. It goes from +2 oxidation state to +1. Correct? And when the reduction is happening for copper +2 ion, it means reduction is happening for Fehling solution. Correct? So Fehling solution is reduced. Who is reducing the Fehling solution? Obviously the aldehyde, and aldehyde belongs to what? Glucose. So that means glucose molecule is a reducing sugar. So glucose is your reducing sugar because glucose contains aldehyde. Aldehyde will interact with Fehling solution, and this aldehyde group will convert actually copper +2 into copper +1. That is from +2 to +1. That is decrease in oxidation state, which is called as reduction, which means the glucose reduces the Fehling solution, the copper of Fehling solution from +2 to +1. Yes? So that means our glucose is a reducing sugar because it reduces the Fehling solution. But which part of Fehling solution? Copper from +2 to +1. Glucose is also a reducing sugar because it can reduce Tollens reagent. How? It reduces the silver of Tollens reagent from +1 to 0. The same glucose can reduce the copper of Fehling solution from +2 to +1. That's why glucose is considered to be as reducing sugar. I hope you have understood, my dear friends. So I will write down one more point here. Aldehyde. You know that aldehyde is present here in glucose molecule. So aldehyde reduces which thing? Copper. Copper +2 to copper +1. Okay? In this much is enough. Aldehyde reduces copper +2 to +1, and this copper +2 is present in Fehling solution. And remember this complex which I have written here, this complex is basically an unstable complex. It's basically a coordination complex. You will study it in coordination chemistry. But remember this complex is an unstable complex right out here. I hope you have understood that what does glucose can do. Glucose can reduce the Tollens reagent. How? It can reduce the silver in Tollens reagent from +1 to 0. Correct? The same glucose can reduce the Fehling solution, the copper in Fehling solution from +2 to +1. But which part of glucose is doing the magic? It's not the glucose actually, it is basically the aldehyde group, free aldehyde group of glucose, which is reducing the copper from +2 to +1 in Fehling solution, and the same aldehyde of glucose, okay, is reducing the silver of Tollens reagent from +1 to 0. I hope you have understood. That's why it will be considered as reducing sugar. So my dear friends, now you have understood reducing sugars. What are those? They can reduce, okay, silver in Tollens reagent from Ag plus to Ag 0. Remember this thing. So my second point is that they can reduce copper in Fehling solution from copper +2 to copper +1. So with these points we can understand what the reducing sugars are. So reducing sugars can reduce silver from +1 to 0 and copper from +2 to +1, okay, in Tollens reagent and Fallings solution. So now what are the conditions for a sugar to be reducing? Conditions for a sugar to be reducing in nature. So let us see what are the conditions for a sugar to be reducing in nature. Is basically, the first is it should have an aldehyde group. Aldehyde is required. Second point is that it should have alpha hydroxy ketone. It should have alpha hydroxy ketone. So this sugar will be also reducing sugar. It should have hemiacetyl carbon. This is also a reducing sugar. It should have a hemiketyl carbon. For your kind information, I will write down this hemiacetyl carbon is basically your anomeric carbon. Anomeric carbon, that is C1 in your glucose molecule, if you remember that. And this hemiketyl carbon is basically anomeric carbon which was there. It's a C2 carbon in fructose molecule. Okay, my dear friends. So if any sugar does have an aldehyde group, alpha hydroxy ketonic group, or hemiacetyl carbon or hemiketyl carbon, if any of these groups are present in a particular sugar, that sugar will be reducing in nature. That sugar can reduce the Tollens reagent and Fallings solution. Tollens reagent means here silver will be reduced from +1 to 0, and in Fallings solution copper will be reduced from +2 to 1. Yes? So my dear friends, what are the conditions for a sugar molecule to be a reducing sugar? I told you that it should have a free aldehyde group, it should have alpha hydroxy ketone, or it should have hemiacetyl carbon, or it should have a hemiketyl carbon in it. So let us understand these 4 examples one by one. Okay, my dear friends, are you ready? Yeah. So let us see here first of all free aldehyde. If you have CHO, CHOH 4 times, then CH2OH. This is our glucose molecule and it does have a free aldehyde here. So you have an aldehyde group here. So this guy will be a reducing sugar. So glucose is a reducing sugar. So what is the role of reducing sugar? It can reduce silver from +1 to 0 and copper from +2 to +1. Okay, let's talk about the second molecule here. If we talk about this particular thing here, okay, CH2OH. This is okay. If I talk about this is again the free aldehyde. Here also we have free aldehyde. This is known as glycerol aldehyde. And this is a monosaccharide. This is also a reducing sugar because it contains a free aldehyde group, reducing sugar. I hope you have understood, my dear friends. Let's take few more examples here. So this was about aldehyde, free aldehyde group. So this was about free aldehyde. Point number 1. Please make note of this. Correct? Let's take second example, which can be a reducing sugar, is alpha hydroxy ketone can be also a reducing sugar if any sugar contains this group. Correct? So which sugar is there? Have a look. You have CH2OH, then C double bond O, then CHOH whole thrice, then you have CH2OH. Let's count it: 3, 4, 5 and 6. Correct? This guy is your fructose molecule. And you know that this is a functional group, ketone. This is ketone, a functional group. Okay, what is this OH group? Which carbon is this? This is alpha carbon. How it's alpha carbon? Any carbon which is adjacent to the functional group. A carbon, here it's 1, 2 and these are 3 and this is 1 last. 1, 2, 3, 4, 5, and this one is 6, correct? A carbon which is adjacent to a functional group is said to be alpha carbon, correct? So this is our alpha carbon. What is present on alpha carbon? On alpha carbon, look here once again, this is functional group, this is carbon adjacent to the functional group, so this is alpha carbon. On alpha carbon we have OH group, so I will call it as alpha hydroxy, and this guy is ketone, so alpha hydroxy ketone. So alpha hydroxy ketonic group is here, so this will be also the reducing sugar. What happens to this particular molecule actually? It undergoes tautomerization and changes into the aldehyde group later. Then it gives the test, correct? So we need not to go in that much detail here. So alpha hydroxy ketone is here. So fructose is a reducing sugar, correct? Let's talk about now third point, that is hemiacetal. Okay, this is your hemiacetal form here. We have a hemiacetal form. A carbon should have OH, OR, and R and H group, correct? Let's have a look. We have to draw the glucose molecule here. Look at the first carbon of the glucose molecule. This first carbon of glucose molecule, that was H, OH, OH, H, OH, H, H, and finally you have CH2OH. This is your glucose molecule. Look at the first carbon. I have told you already that first carbon is the anomeric carbon, and this first carbon is also known as hemiacetal carbon or cyclic hemiacetal carbon, also known as anomeric carbon. Anomeric carbon. It should fit into this structure. Have a look. Carbon should be having OH group, H group, R group, and OR group. Look here. This carbon has H, OH, OR, because this is your O and this is carbon is R. So carbon with H, OH, and downwards also there is a carbon. So look at this carbon. What is here? H, OH. Here is also H and OH on this carbon. This side O and R. This side R. So this side OR and this side R. This is actually an ether, but I don't want to tell it in ether here. So it does have a hemiacetal carbon. And this is our glucose molecule. Again, we can say that it's a reducing sugar. Okay. Let me draw the structure of fructose molecule. So let us draw it in this way. Cool. So here we can have OH and here we can have CH2OH. That's first carbon, second carbon, third. Then you have fourth. Fifth carbon you have here. CH2OH. That is the sixth carbon. Fifth, fourth, third. Now my dear friends, the second carbon is basically here. Which carbon? Hemiketal carbon. This is also known as, I can call it as hemiketal carbon, and it's also an anomeric carbon in fructose. Anomeric carbon. Correct? So look here. For hemiketal carbon, you should have R group. 2 R groups should be there. So this is one R group here for this carbon. Second carbon, this is R group. This side also one more carbon is here. This is R group. So R and R we have. On the other side we should have OH, RR, and we should have OH. So OH is here. And another group should be OR. So this is O and this is R. So here you have OH, R, R, and OR. So this is your hemiketal carbon, also known as anomeric carbon in fructose. So it will be also a reducing sugar. So fructose is also a reducing sugar. I hope you have understood, my dear friends. This is all for today. Have a good time. Yo-yo. Thank you.